The moment it happens, nothing explodes, nothing burns, and there is no dramatic warning. The lights simply die. Across entire cities, power grids fall silent in less than a second. Phones shut down, vehicles stall, transformers fail, and the invisible backbone of modern civilization collapses into darkness. This is the realistic consequence of an electromagnetic pulse, or EMP, an intense burst of electromagnetic energy, capable of overwhelming electrical systems across vast geographic areas. It is not science fiction, it is physics interacting with infrastructure built for efficiency, not resilience. And the real danger is not the flash itself. It is what happens in the hours and days after the grid stops responding. To understand the threat, we have to analyze how modern electrical systems operate. The power grid depends on synchronized generation, long-distance transmission lines, and sensitive electronic control systems. High-voltage transformers regulate energy across regions, but these components were designed decades ago under assumptions of predictable electrical environments. An EMP introduces a sudden surge of electromagnetic energy that induces powerful currents in long conductors such as transmission lines, antennas, and even household wiring. These currents overload control electronics and protective relays faster than automated safeguards can react. The grid doesn't simply trip offline, it can suffer hardware damage that takes months or even years to replace. A common misunderstanding is that EMP damage only affects military targets or advanced electronics. In reality, the vulnerability lies in scale and connectivity. Long transmission lines act like giant antennas during a geomagnetic disturbance or high-altitude electromagnetic event, channeling destructive currents directly into transformers. These transformers are massive, custom-built machines that cannot be replaced quickly. Manufacturing one can take over a year, and transportation requires specialized logistics. When multiple units fail simultaneously, restoration becomes a slow engineering challenge rather than a quick repair. The overlooked science lies in electromagnetic coupling. Energy from an EMP interacts with conductive structures, converting invisible radiation into damaging electrical surges. Research conducted by institutions such as NASA and NOAA has shown that natural geomagnetic storms can already induce grid-damaging currents during intense solar activity. Events similar to the historic disturbance observed by Richard Carrington in 1859 demonstrated that large-scale electromagnetic disturbances are not hypothetical. They are part of natural space weather. The survival implication is not immediate destruction, but prolonged systemic failure. Without grid electricity, water treatment facilities stop pumping, fuel distribution halts, refrigerated supply chains collapse, and communication networks degrade rapidly. Within 72 hours, modern urban environments begin to experience cascading infrastructure failure. As the blackout continues, the deeper engineering consequences begin to surface. Electrical grids are not isolated machines, but tightly synchronized systems operating at precise frequencies. When a large portion of the network collapses simultaneously, restarting it becomes far more complicated than simply flipping switches back on. Grid restoration requires a process known as black start, where small generating units are used to sequentially re-energize transmission networks and restart larger power plants. The danger is that this procedure assumes critical hardware remains intact. If transformers, control electronics, and substations have been physically damaged by induced currents, the black start pathway becomes fragmented or impossible. A common misunderstanding is that backup generators will simply maintain operations until repairs occur. In reality, most generators depend on automated electronics, fuel deliveries, and cooling systems tied directly to the grid. Hospitals, communication towers, and water treatment plants may operate for hours or days, but once fuel logistics fail, those generators fall silent as well. This reveals the hidden engineering reality of modern infrastructure. Redundancy exists for short-term outages, not for the prolonged absence of the grid itself. The overlooked science involves geomagnetically induced currents, often abbreviated as GICs. During strong electromagnetic disturbances, fluctuations in Earth's magnetic field create slow-moving electrical currents in the ground. These currents travel through transmission networks and concentrate inside transformer cores, causing overheating, insulation breakdown, and permanent damage. Studies conducted by the Electric Power Research Institute and monitoring programs run through the United States Geological Survey show that even moderate geomagnetic events can push transformers beyond safe operating limits. The threat is not theoretical physics, but a documented interaction between space weather and industrial infrastructure. Evidence of this vulnerability appeared in March of 1989 when a geomagnetic storm disabled large sections of the Hydro-Quebec power grid in Canada within 90 seconds. Millions lost electricity not because equipment exploded, but because protective systems detected abnormal currents and shut down the network to prevent catastrophic damage. That event was far smaller than the disturbances recorded during the 19th century, yet it demonstrated how rapidly a grid can unravel when electromagnetic forces overwhelm engineered safeguards. For survival planning, the implications are systemic rather than local. When electricity disappears, modern supply chains begin to fracture almost immediately. Fuel pumps require power. Telecommunications rely on data centers and fiber amplification nodes that require continuous electricity. Urban water distribution depends on electric pumping stations to maintain pressure. Without these systems, even well-prepared communities begin to face cascading shortages within days. The escalation emerges when infrastructure failures interact with human behavior. As communication networks degrade and transportation systems stall, coordination becomes difficult. Emergency services rely on digital dispatch networks and GPS timing signals, both of which can be disrupted by electromagnetic disturbances. What begins as a silent electrical anomaly gradually transforms into a widespread logistical crisis. And this is where the final reality becomes clear. The true threat of an EMP blackout is not the moment the lights go out, but the complex, fragile systems that stop functioning afterward.